Okay, good evening, everyone. Can you hear me? Can you see my screen? So for those people that are watching us on YouTube, you can just send the message to the YouTube chat box. But for those in-house team, can you hear me? Can you see my screen?
Yes, sir. We can hear you, sir, and see your screen, sir.
Oh, good. Oh, good. So let's start. Tonight we're going to be looking at what we call a logistic regression. A logistic regression. What do we understand by the logistic regression? So I'm going to be taking it step by step, so that we won't bother ourselves too much. Now, have you ever thought of it that if I have two possible outcomes, what did I mean by two possible outcomes? That is, let's say for instance now, you want to write a particular exam. Two things will come to your mind. Is either you pass that exam or the person did not pass that exam. That's two outcomes. Now, let's say for instance now, you went for a test. Let's say a test of a particular, let's say malaria, for instance. Two things will come to your mind. Is either the malaria is positive or negative. Now, for those people in our Greek, let's say you plant a particular crop. Is either the crop germinates very well or not. So, the outcome is binary. That is, the result that you are expecting is binary. Is either they pass the exam or they did not. Is that the test tested positive or negative? So, anytime you have a binary outcome, anytime you have a binary outcome, then there is a need for us to develop a model that can capture the binary outcome. We have a lot of we have several models that are linear. Let's say simple linear regression. At that point, the outcome of a simple linear regression is a number. That is, give me your age, I'm going to predict your weight. Your weight is a number. Or let's say for instance now, give me your diet, I'm going to predict your systolic blood pressure. Now, at that point, the outcome can be greater than 1. That is, you can have a systolic blood pressure of, let's say, 200, 250. I'm just using that as an example. They now want to model, we want to think of how we can have an outcome that is going to be binary. It's either yes or no. And then we want to predict the probability of that outcome. We want to predict that probability of outcome. Please note that from tonight that the probability always takes its value from 0 and 1. You can't have a probability value that is less than 0. And you can't have a probability value that is greater than 1. So those are the things that they observe. That let's say we want to model two outcomes. We want to model two outcomes. Dora, for me, please mute your mic. I've muted everybody, please. Okay. So if you are trying to model that, it's either the disease is present or not. So if the disease is present, so that means that the probability is 1. Oh, we are certain that the disease is present. But if the disease is not present, that means that the probability is equal to 0. Now, to now model this, they now think of which model can we use, because the existing model, they can predict above 1. Let's say, for instance, now I want to predict your weight based on the height. Automatically, your weight will be greater than 1. So they now think of which model can we use to predict two binary outcome. It's either they pass the exam or they did not pass. It's either the test is positive or negative. It's either the crop yield very well or not. For those people in law, it's either they win the case or they did not. So they now think of what can we do to model all this situation. That is how they now come up with with a logistic regression model. So logistic regression model is a probability. We normally use the probability like the log of odd. So I'm going to be taking us through. That is just the simple scenario or the simple analogy to explain the logistic regression. So please take note that anytime you want to use a logistic regression, you must know that your outcome is binary. You have just two possible outcomes. It's either yes or no. It's either the disease is present or absent. So anytime you are having that as your outcome, then you can model it with what? With logistic regression. There are a lot of things that guide logistic regression, which we are going to be checking tonight. Now, this is the learning objectives. This is the learning objectives. Number one, at the end of this class, you should be able to explain the concept of logistic regression, and is what is sustainability for modeling binary outcome in biomedical, public health, clinical research, or in other fields. So at the end of this, remember I told us that this lecture is going to be 4 series. This one that we are starting tonight is I'm going to introduce us to the logistic regression and then the mathematical part of it and statistical part of it. Remember I told us that for data scientists, if you want to be a good data scientist, you must know a bit of algebra, you must know a bit of calculus, you must know a bit of matrix, you must know a bit of statistics, how to formulate a model. Because as a data scientist, you are automatically a data analyst. Data analysis is a subset of data science. So if you are a data scientist, that means that you automatically you are data analyst. But data analyst is not equivalent to data scientist. The converse don't hold. Now, the objective is that at the end of the lecture, you should be able to describe the mathematical base of the sigmoid. Sigmoid is a function of logistic regression, which I'm going to be showing us tonight. It's a function, and then it is sigmoid that we normally use in machine learning that we call activation function. I don't know, maybe we've heard about the activation function. The activation function is the one that activates the output, whether to predict yes or to predict no. So anytime you want to do a classification in machine learning, you want to classify, it's either the diabetes is present or the diabetes is not present. It's either you make huge sale or you don't make huge sale. And you want to model it, you want to develop a machine learning model. We normally use a sigmoid activation function. That is, it gives two response, two binary. It's either yes or what or no. So we normally use a sigmoid function. So a sigmoid function is a function from the logistic regression. Just be taking note of that. And then the number 3, that at the end of this, you should be able to differentiate between linear regression model and the logistic regression model. You should be able to work to differentiate between the linear model and then the logistic regression model. And lastly, you should be able to interpret the logistic regression coefficient in terms of the log odd, in terms of the odd ratio, and then the practical aspect of it in the real life situation. So starting from our subsequent one next week, Sunday, we are going to be going deeply into the R. We're going to be using the R Studio to demonstrate this. So we're going to be using a real life data set. So by the time we get to that stage, you won't be asking me, oh, how do we normally interpret the odd ratio? How do we get the odd? What is the meaning of the odd? And some other things like that. So you will not be asking me that. And let me also state this expressly, that as a team of Donwell Data School, you can be a point to take any of this course. So that is why we have to equip ourselves with a good knowledge and grant ourselves with a good knowledge of this. So the subsequent one is going to be purely practical, and that one we're not going to stream that one online. So if anybody wants to join the team, we have procedure for that. You must be participate in one of our data camp. So after that, you can write to the team that you want to be part of us, and then we have people that is going to that are going to screen your application. Then if it's okay, you are going to be admitted to the team. So let's keep the ball rolling. Now, introduction to logistic regression. Logistic regression is a statistical modeling techniques used when the dependent variable is binary. Remember that anytime you are hearing the word dependent variable, the dependent variable is the same thing as your outcome variable. Dependent variable is the same thing as your response variable. So when you have the dependent variable to be dichotomous, to be binary, then you have we normally use a logistic regression. For example, if I ask you, are you going to be in UI tomorrow? It's either you tell me that yes or no. Then if you go for a screening, if you are screening people for a particular disease, it's either the disease is present or no disease. It's either someone is alive or dead. It's either success or failure. So anytime you are having that, you are having the binary responses like this, then we have the a model called the logistic regression model. The logistic regression model. Please take note of that. It's very, very important. Immediately you check your outcome variable and you see that your outcome variable has just two responses. It's either yes or no. So irrespective of your field, it's either a student pass or fail. Then you will model it with a logistic regression model. Unlike linear regression, which predicts a continuous outcome. Now, linear regression, we normally use linear regression to predict continuous outcome. And then when I'm talking about the continuous outcome, I'm talking about the numeric value. We normally use it to get the numeric value that are continuous. Remember, I've explained the concept of discrete and continuous. When we are talking about the discrete variable or discrete data are the count data. Let's say, for instance, 1, 2, 3, 4, 5, 6. It is called discrete. But when we are talking about the continuous simply means that it takes its value on a number line. What did I mean by a number line? From 0 to 1, we have billions of numbers. We have 0.01, we may have 0.002, we may have 0.004, we may have 0.006. So they are continuous. So the normal linear regression predicts what? Predict the continuous value. So that is why if you have a simple linear regression that I want to predict your weight based on your height, your weight can be 5 point something, it's still continue. It's a continuous value. It can be 6 point something, it's a continuous value. It can be 80 point something, it's a continuous value. So in that sense, we normally use simple linear regression. But logistic regression predict the probability. I want you to have that mindset that if you are dealing with the logistic regression, you are working with the probability. The probability of the outcome belong to a particular class. Let's say, for instance, now I want to tell what is the probability that this particular group of students, they are going to score above 80. It's either they score above 80 or they don't score above 80. So the class is either what? We code it as 1 and 0. Now, let me also say this, that in logistic regression, if you are coding it, you are going to code it as 1 and 0. For those people in computer science, anytime you are hearing the word 1 means on, while 0 means off. Please take note of that. So for your system, whether you are using R programming language or you are using Python as a data scientist, for those systems to understand that you want to use a logistic regression model, your dependent variable has to be coded as 0 and 1. 0 and 1. So anytime you are coding it as 1, it means that that person is going to score above 80% in that exam. So the probability of scoring above the 80% in the exam, and then 0 means that he's not going to score up to 80% in the exam. So logistic regression, it takes its value from what? It dichotomizes it to be 1 and 0. But our normal linear regression, we can have a continuous value. Now, why logistic regression is important across discipline? You may ask yourself, why is logistic regression important? Many real-world decisions are binary in nature. Logistic regression helps us to helps quantify and model this decision if it is widely used across our various fields. Look at the public health. So I really took my time to prepare this slide because I want this slide to be across all field. Across all field. So you can use logistic regression irrespective of your field. Now, in public health, let's say for instance that you want to check whether someone they have tuberculosis, that is TB. Is it that the tuberculosis is present or not? So that is why I'm having yes or no. Is it that the tuberculosis is what? Is present or not? In the area of medicine, let's say we want to check the mortality. Is it that the baby is alive or not? So if you want to model that, what is the cause of mortality? What are the things that are contributing to the mortality? So you can model the outcome. The outcome is binary, so you have to model it with the logistic regression. So that one is going to give you what are the factors that are contributing to the death of infants. So you can model that using logistic regression model. Now, in education, you may want to model what are the things that are contributing to a student being passed very well in mathematics or in English language. Is it the teaching style? Is it the hours of teaching? Is it the CA that they have? We can use logistic regression to model that. In agriculture, you may want to check if a particular fertilizer is effective by checking the yield on the crop. So if that fertilizer is effective, it's going to be yes, and if not, it's going to be what? It's going to be no. In law, for law students, for those people that study law, because now lawyers are now what? They are now going to data science, because based on all their data they've gathered, they should be able to predict if they are going to win a particular case before they even go to court. So they are now into data science now, law. So now in law, you can predict if the bail will be granted or not based on the what? Based on the level of that what? Of that offense. So is it that they granted you the bail or not? So you can dichotomize that. Now in business or marketing, you can check the purchase made. And also in engineering, you can check the component of failure. Is it that this particular engine is going to fail or not? So logistic regression is applicable in all field of interest. So that is why as a data scientist, you have to be all round. You have to be all round. If they are bringing the data of telecommunication, you should be able to handle it. If they are bringing the data of health, you should be able to handle it. If they are bringing the data from education, you should be able to handle it. If they are bringing data from agri, you should be able to handle it. So that is why I did not streamline to one particular field. So as a data scientist, we are the intersection across all fields. What did I mean by that? Every field depends on us. So that means that you have to widen your knowledge as a data scientist, not as a data analyst, but as a data what? As a data scientist. Now, this is where we are going to go a bit down into mathematics. Mathematical foundation of logistic regression. The reason why I have to take you through this is that this is what happened at the back end. If you just type you just write a 2 lines of code and you see the result. What is at the background of that system? And as a data scientist, you have to know both the back end and the front end. Ordinary data analysts, they just prefer the front end. Let me just put the data inside my what? Inside my system, and then I will get my result. They are less concerned about what is happening at the back end. But you, as a data scientist, you should be able to know what is going on inside and what is coming out, so that if there is even any error in the output, you should be able to know where to trace it to. So that is why I have to expose our eyes to this mathematical concept. And as a data scientist, if you want to be a good data scientist, you must have a little knowledge of mathematics, a little knowledge of statistics, and then you have to be grounded in algebra, which is very, very important. So I'm going to be taking us through little by little that we can take, because I know that it's not everybody that they have mathematical background or statistical background, but just have that mindset that I'm a data scientist. And for you to be a good data scientist, you must have the knowledge of mathematics, which is very, very important. Now let's go to I'm going to start with the concept of probability, because before we can get to logistic regression, there are steps. So the list in the hierarchy of the step before you get to logistic regression is the probability. Now, what do you understand by the probability? Probability is the measure of how likely something is to happen. Let's say, for instance, if I ask you that, what is the probability that tomorrow is going to be Monday? You are certain that tomorrow is going to be Monday. You will tell me that the probability is 1. Now, if I ask you that, what is the probability that you are going to finish your exam in the next 1 week? Or what is the probability that in taking any exam, you are going to have an A1? If I ask you that, what's the probability that it's going to rain tomorrow? What is the probability that I'm going to get to my place of work before 8 p.m. tomorrow? So probability is the day-to-day activities that we normally perform, that but we don't know. So probability is the measure of how likely something is going to happen. We don't really sure that, oh, this thing is going to happen, but we know that there is possibility that it's going to happen. If I ask you that, what's the probability that it's going to rain tomorrow? But for those people into weather forecast, they can check and tell us that, oh, the probability that it's going to rain tomorrow is 90%. That is, the probability is higher that it's going to rain tomorrow, but they are not even certain, because it is when you are certain that it's going to rain tomorrow is 1. So it is only God that has that certainty. So we model, we use probability in our day-to-day activities. So, and then probability ranges from 1 to 0. The value of probability is between 0 and 1. That is, you can't have a value of probability that is less than 0, and you can't have a value of probability that is greater than 1. Please, I want us to take note of that. So that is why we normally use probability in logistic regression. So unlike the other model, you can have a value that is less than 1, that is greater than 1. You can have a value that is less than 0. But in probability, you don't have value that is greater than 1, or the value that is less than what? That is less than 0. So once you have that, then look at the example that I have here. If I ask you that, oh, in a toss of a coin, if I flip a coin, what is the probability of getting head? What is the probability of getting head? I can say, oh, the probability of getting head in a flip of a coin is half, which is 0.5. That is, if I have a coin, we have 2 possible outcomes. It's either head or tail. So inside that possible outcome, the probability of getting head is going to be, how many head do we have there? We have just 1 head, divided by how many outcomes do we have? It's either head or tail. We have 2. So 1 divided by 2 is going to give us 0.5. So I will tell you that if you flip a coin, the probability of you getting head is 0.5. If you flip a particular coin, the probability of you getting tail is 0.5. If I ask you, what is the probability that is going to rain tomorrow? You can tell me that the probability that is going to rain tomorrow is 0.8, which is 80%. That you have 80% assurance that it's going to rain tomorrow. If I ask you that, what is the probability that a particular student is going to pass this exam? You can tell me that the probability that this student is going to pass this exam is 0.9, which is the same as the 90%. That is, you are 90% sure, maybe based on the preparation of that student, or based on the test that student he or she have scored in the test, that you are also sure that it's going to pass the exam. So those are the examples under probability. So in logistic regression, we want to predict. Now, I want to be joining them together now. In logistic regression, we want to predict the probability that a certain event will occur. Will the patient recover from a particular sickness? We want to predict the probability. What is the probability that the way you are giving this patient drug, the treatment, the intervention, what is the probability that this patient is going to survive? We may want to check what is the probability that the person that borrow a particular money, a loan, borrow particular loan, is going to return it, or loan default. You may also want to check what is the probability that the event of a student being pass or fail. Will a student pass this exam? So in logistic regression, probability is the foundation. If you have a good knowledge of probability, you won't have a difficulty in handle regression model. So those are the things that we normally check in carry out the regression. That's what we call a guide to logistic regression. Let's move on, please. If you have questions, you can just raise up your hand, and then I'm going to check the YouTube to see if you have people that they have questions there. Now, you may ask yourself, although I've explained it, why can't we use linear regression for this? Why can't we use linear regression to predict if someone will pass the exam or not? Now, let me start with the simple linear regression. In a linear regression, we use a straight line equation. If you remember from your secondary school, we normally have equation of line, that is y is equal to mx plus c. Now, the y there is what we call the dependent variable. That is what you want to predict. And then the beta node that you are seeing here is the same thing as your intercept that you normally have in your secondary school mathematics. That is equation of line. Now, the beta 1 that you are seeing here is what we call the coefficient of the x. That is the coefficient of your independent variable. And then we normally introduce here, although in secondary school we don't introduce error. So, but now you are now in advance. Then we now introduce error. This is what we call the error term. That is the possible error that may occur if you are using this model. Now, the equation can give any number. This equation that you are seeing, you can predict any number. That is, supply me the value of x. After I've calculated for beta naught and beta 1, supply me the value of x, I'm going to predict y. So y can come out as any number. You may have 2 point something, you may have 3 point something, you may have 500. Y can come out as any number. And then the number is what can below 0 or above 1. So this equation 1 that you are seeing can give you any number that below 0 or above 1. But probabilities must be between 0 and 1. Remember, the probability must be what? Must be between 0 and 1. So we need a function that force the outcome to stay between 0 and 1. That is the brain behind logistic regression. They need a particular function that can take between 0 and 1. That will not go out of that band. But if you use the simple linear regression model in equation 1, you can have a result or a response that is out of that band. So that is why we need the logistic function, which is also called the sigmoid function. That is the origin of the logistic regression. We need the outcome between 0 and 1. But all this outcome, all this model that we have so far, some may be above 0, maybe below 0, some may be above 1. Can we get something that will give us the outcome between 0 and 1? So then they now think of what the logistic regression model. Now, let me quickly take us to what we call the sigmoid function. A sigmoid function looks like an S-shape curve, and it is defined as this. Now, the probability that this outcome y, this is y. Remember, from our equation here, we have y here. So y here is the outcome. Now, when you have an outcome to be 1, so that means that it is positive. When you have your y to be equal to 1, so that means it's positive. Now, you want to check what is the probability that this person will tested to this disease, or what is the probability that this person is going to pass the exam. Remember, if the person passed the exam, so that means that your outcome will come out to be 1. If the person did not pass the exam, that means that your outcome will come out to be 0. Now, we now want to predict what is the probability that this person is going to pass this exam, or what is the probability that this person is going to be tested positive to COVID-19, or what is the probability that this particular lawyer is going to win this case, or what is the probability that this particular engineer, the engine that they've produced, is going to work for 10 years. So if the engine works for 10 years, that means that your outcome is 1. If the engine does not work to 10 years, that means that your outcome is 0. If the lawyer win that particular case, that means that your outcome is 1. If the lawyer did not win that particular case, that means that your outcome is 0. So now, we now want to check what is the probability that this lawyer is going to win this case? Or what is the probability that the person that maybe went for a particular screening of a COVID-19 is going to be tested positive? So the probability is now what? We have 1 divided by 1 plus the exponential of minus z. Exponential of minus z. Now, what is now that z? Now, let us now come back to our equation 1. Now, if you look at this equation 1, it is called simple linear regression. Why do we call it simple? We call it simple because we have just one dependent variable x and one independent variable. We have one independent variable x and one dependent variable y. It is called simple linear regression. But immediately your independent variable is more than 1. Immediately your independent variable is more than 1. That is, we want to check we want to predict your weight based on your age, based on your diet, based on the level of exercise. So we have independent variable that is more than 1. So immediately you have the independent variable that is more than 1. It is no longer a simple linear regression, but a multiple linear regression. A multiple linear regression. Now let's go back to equation 2. If you look at this equation 2, which is the probability that this particular event occur, we now have what? 1 minus 1 divided by 1 plus the exponential of what? Minus z. Why this z are those combination of independent variable that you have. Look at my z. My z is now what? The beta naught plus beta 1 x1, which is the independent variable 1, and then plus beta 2 x2, which is independent variable 1, up to the beta n xn, as many independent variable as possible. Now let me now bring this back to a real life situation. Let's say, for instance, now I want to predict whether someone is going to be a diabetes is present or not. I want to predict the probability of what? Coming out to be a diabetes patient, or coming out to be a positive to high blood, let me say high blood pressure. Now, if it is high blood pressure, it's going to be 1. If it is low blood pressure, it's going to be 0. Let's say, for instance, that I want to predict someone passed the exam or not. If you pass the exam, it's going to be 1. Now, if I want to predict that, what is the probability that you are passing this exam? Then all these beta 1, beta 2 are the coefficient of the independent variable, all those factors. Let's say, for instance, now the x1 here is the test score that you have, the variable that capture your test score. The x2 here is the variable that capture the hours of study. Then let's say, for instance, I have the x3, the time that you spend, or the food that you take, or how you use your brain. So if I take everything here, it's going to give me the value for z. So if I have all those predictions here, if I have those values here, I'm going to have value for z. So immediately you have the value for z. Now taking the value of z into this equation here is going to give you the probability that that person is going to pass the exam or not. So the P is the probability of the event happening. That is, yes, this person passed the exam. Yes, this person tested to COVID-19. Yes, this machine worked for more than 10 years. Yes, this particular lawyer he won, or is going to win the case. So the E that you are seeing here is the same as your exponential. Exponential here is what we call the Euler number. Euler is one of the great mathematicians. So the value is 2.718, but you don't need all this. This one is just the theoretical part. Those things that we normally, when you press it inside, when you write the code, then you just see the result. Those are the things that they've inputted in those systems. And if you are developing a model, because as a data scientist, the difference between you and data analysis is that you can develop a model. You can write your own model from scratch. So by the time you are writing your model from scratch, you are taking some parameter. You must know how to input all this value. You must first of all write out those equations, solve those equations numerically before you now translate it to a model. Before you now translate it to a model. So those are the things that you have to know as a data scientist. I'm not training you to be a data analyst. No, I'm training you to be a data scientist, and then you should be able to develop a model. So as a data scientist, you are automatically a data analyst, because data analysis is a subset of data science. Please take note of that. So this function squeeze any number, positive or negative, into 0 and 1. And it is perfect to model for modeling probability. For modeling probability. So this is the sigmoid function. This is the sigmoid what? This is the sigmoid function. So it takes its value. Look at where I have this 0. It takes its value from 0 to 1. From 0 to 1. It predicts 0 to 1. Look at this. This is 0. You can't see value that is less than 0 here. If you look at this, my y-axis, the maximum here is 1 and the minimum here is 0. So this is the sigmoid what? The sigmoid function. The x that you are seeing here is the same thing as our z that I explained in our previous slide. So this is the S shape that I mentioned about the sigmoid what? The sigmoid function. So it takes its value from what? From 0 or to 1. So we normally use this to model the probability outcome. Now, we want to move now from probability to odds. We want to move from probability to what? To odds. But before that, I think I've spent like 45 minutes. Can I welcome 2-3 questions, please? If you have questions, just raise up your hand. And then if you are joining us from YouTube, let me log into my YouTube now so that I can pick up your question. If you have any question for me, and then for those people, for those in-house, please, if you have question, let me have your question. Let me have your question. Mr. Lide, any question?
No question from my end, sir.
Okay. Ibukun, any question for me?
No question, sir.
Mommy Adebisi, any question for me? Although you joined late. Any question for me? Babalola Timileyin, any question for me?
No question for now, sir.
Oh, good. Damilola, any question for me?
No question, sir.
Oh, good. Olayinka, Boluwatife, any question for me?
Not for my name now.
Okay, good. Dolafumi, any question for me?
No questions, sir.
Okay, good. Oh, good. Let's check our YouTube channel and let's see if you have any question. If you have any question, you can drop it on our on our page. So I'm going to read it out. So while waiting for your question, so let's move on, please. Now we've established the probability. Now we want to move a step further by checking what we call the odds. Maybe we've heard about the odds before, odd ratio, whatever. Okay. So now, odds are another way of expressing probability. Is another way to express the probability. Now, odds simply means that the probability of success divided by the probability of failure. Let's say, for instance, now, if I ask you what is the probability that is going to rain tomorrow, let's say I give you the probability that, okay, the probability that is going to rain tomorrow is 0.8. That is 80%. So if I want to get the odd of raining tomorrow, the odd that is going to rain tomorrow is going to be the probability that is going to rain tomorrow divided by 1 minus probability that is going to rain tomorrow. And remember, if I have probability of success, the probability of success for the probability of failure is equals to 1. So by the time I have P divided by 1 minus P, I'm going to have what? I'm going to have 4 here. This tells us that the probability of raining tomorrow is 4 times higher than the probability of no rain. what is the meaning of this in a layman language? There is 80% chance that it will rain tomorrow, and then the odd of rain is 4 to 1. Now, let's say, for instance, now, let's say I'm counting this from today. If it did not rain today, and I have the odds to be 4, that is, if it did not rain today, in the next 4 days, Monday, Tuesday, Wednesday, Thursday, is going to rain. That is what this one is telling us. The odd. Let's say, for instance, now, what is the probability? If the odd of you passing this particular exam is 5. Now, it means that if anybody failed that exam, if that person failed the exam that does once, it has the higher chances of passing it in 5 times subsequently. I'm trying to look at how I can still explain the odd for you. Now, that is why those people that normally play betting, those Bet Nigeria or whatever, the sports betting and some other things, they'll be talking about the odd. The odd of winning is 4.5. The odd of winning is 7. The odd of winning is 8. How did they come about that odd? It means that they've checked over the year, they've checked the probability of those teams winning. If the probability that those teams winning in a way is 70%, that is based on their past record. Let's say, for instance, now they've had 10 matches away, and out of that 10 matches, they've won 7. So that means that they have 70% probability that if they go away to go and play away ball, they are going to win. 70% chance. Now, you can now model and check the odd that they are going to win. So to check the odd now, it's going to be what? 70%, 0.7 divided by what? 1 minus 0.7, which is going to give you 0.7 divided by 0.2. By the time you do that, you are going to get the odd of winning. So that is why if you see all those guys, they will go to all those betting shops, they will be asking, please, what is the odd that this particular team is going to win? They will just say them the odd is 4:1. That is, they have 4 times likely to win that match rather than losing. That is, if they lose that match once, they have 4 times of winning. So that means that out of if they are having 5 matches away, there is higher probability that they are going to win 4 and lose 1. So that is why they normally ask, what is the odd? What is the odd? What is the odd? But those people that they normally ask for the odd, they don't know the foundation of the odd. So everything is still boiled down to the probability. Let's say, for instance, now, for those people, maybe they've written UTME like 7 times, like me personally. I wrote UTME 7 times. So let's say, for instance, now they now ask me that, oh, what is the odd of you passing UTME? Now, after the attempt of 7 times, although I did not fail any of them, let us now say, for instance, now I scored above 200. Let's say 5 times. I scored above 200 5 times out of 7 times attempt. Now, the probability of me taking another UTME exam and pass is going to be what? 5 divided by 7. So by the time I have 5 divided by 7, I'm going to have the probability that if I take this exam again, I'm going to pass. So I can now model that probability, that what is the odd of me making an attempt again. So by the time I do that, I can calculate the chance of me passing again. So this is how we normally get the odd. So from probability now to odd. Please just be following me like that. Remember, we started from probability and I take us through the sigmoid function. Our endpoint is the logistic regression. So we are moving now from probability to odd. Now let's continue. Now, we are now moving now from odds to log odd, which we also call the logit. Logistic regression does not model probability directly. Please take note of that. Logistic regression does not model probability directly. It models the log of the odd. Now the odd ratio, the odd that you now have, by the time you now take the log of that odd, then we have the logistic regression. So we have the logit of P, where that P is the same thing as 1 divided by 1 over what? Over P. 1 divided by 1 over P here is what we call the odds. The odds that have shown us in equation 3. So by the time you take the logarithm of the odd, then you have the what? We have the logit. We call it logistic regression. So why log of odd? You may ask yourself, why log of odd? Because the log of odd range from the minus infinity to positive infinity. The log of odd, the result range from the minus infinity to positive infinity. And then remember, from our linear regression, linear regression can, the output can take its value. It may be below 0, it may be more than 0. So it's between minus infinity to positive infinity. Now, for us to now model the linear regression in form of the logistic, we want to inculcate linear regression inside the logistic. It must satisfy the assumption of linearity. So, and then one of the assumptions of linearity is that it takes its value from minus infinity to positive infinity. For us to now capture that, in the what? In our logistic regression, then we normally use the log. If you type the log of positive infinity, it should give you 1. And if you type the log of negative infinity, it's going to give you 0. So that means that we are able to put them in the context of logistic regression that takes its value, that predicts 0 and 1. So, but if you don't take the log, if you don't put log here, we won't be able to capture the linearity into the logistic regression model. Now, number 2, also, it helps us to turn the probability. Also, it helps us to turn the probabilities into a linear function of the input. So once you have the probability, you can use log to turn it to the linear function. So we're going to be seeing that shortly. So the equation 4 is the what? Is the log odd, which we normally call the logit. The logit is very, very important. Now, logistic regression model. Now, this is now the logistic regression model. Now, we have this part here. This is the log odd, the log of odd. And this particular one that you are seeing here is like a linear model. That is, we have beta naught plus beta 1 plus this, and this. So instead of us now having y as our dependent variable now, it will now be the what? The log of odd. So by the time you have this equation 5, this equation 5 is now what we call the logistic regression model. This equation 5 is what we call the what? The logistic regression model. Now, if you want to get the probability, let us now say I have the logistic regression model now, and I want to get the probability. Now, to get the probability, which is in equation 2. Remember, I showed the probability in equation 2. Then we apply what we call the inverse function. Take the value from 0 and 1. Remember, the S shape that I showed you the other time, it takes its value from 0 to 1. It is called the sigmoid function. So the sigmoid function, to get the sigmoid function, which is, we're going to apply the sigmoid function to the equation 5 in order for us to get the probability. Now, if you apply that to this, remember, if the log here cross this equation, anytime the log cross equation, it will turn to exponential. So the log here will turn to exponential and carry all this value. So by the time it carries all this value, we're going to have exponential beta naught plus what? Plus beta 1x1 plus beta 2x2 up to the what? Beta n xn, which is the equation 6. I'm dealing with data scientists. Please, you have to familiarize yourself with all this mathematical equation, and then all this mathematical solving or mathematical manipulation or mathematical function. So by the time we do the inverse, then we are going to have, let's say for instance now, I want to make P the subject of the formula. If I cross this equation and then I do some my manipulation here, I'm going to have equation 7. From equation 6 to equation 7 is like 7 steps, which I have jumped here. 7 steps. Now, I now have my P to be equals to 1 divided by 1 plus exponential minus all this value that I have here. Now, if I assume that all these beta naught and beta 1, if you remember from our equation, let me take us back a bit. Let me take us back a bit. Look at this equation 2 now. If you look at my Z is beta naught, beta plus beta 1 plus beta 1x1 plus beta 2x2 up to beta nxn. So now, it is not that Z. If I now represent that Z back, let's go back to the equation 7. If I now turn this one to Z, if I turn this one now to Z, it's going to be, we now have equation 7, which is a sigmoid function. Equation 7 now will now look like equation 2 that we have here, which is the sigmoid function. But in machine learning and in artificial intelligence, we normally call it the activation function. We call it the sigmoid function and what activation function. So let's go back to equation 7. So the probability now, we can now have this as a probability, which is equation what? Equation 7. Look at how we move. We started from the probability. From probability, we move to what? We move to the odd, the sigmoid function. From the sigmoid function, we move to the odds. So from odd, we move to the log odd, which we call the logit. And then we have our regression, logistic regression equation. Now, this is now where we're going to start our interpretation. How do we now interpret? How do we interpret this? How do we interpret this? So, remember that from the logistic regression, equation 5, we have all these beta naught, beta 1, beta 2, up to beta n. They are called parameters. They are called parameters. When you run your, like yesterday now that we ran a particular logistic regression model, we have those coefficients. That is what we call the parameter. So those parameters are beta 1, beta 2, beta 2. They are called weights in machine learning. They are called what? Weight. If you are hearing the weight. We don't talk about the parameter in what? In machine learning. We call it weight. We call it what? We call it weight. So we call it weight. So all those parameters, the beta naught, the beta 1, beta 2, they are called what? They are called weight. Those are the things that we're going to be interpreting. Now let's look at it. Each beta represents the change in log odd of 1 unit increase in the corresponding variable. Remember that when we want to interpret our linear coefficient, we normally say that, okay, a unit increase in dependent variable will give you let's say if the coefficient, if the beta naught is 2.1, a unit increase in the dependent variable will give you 2.5 times increase in the independent variable. A unit increase in your independent variable will give you 2.5 increase in your dependent variable. So we are interpreting the outcome based on the coefficient, based on the what? Based on the coefficient, based on the what? Based on the weight, the beta that we have. Now, how do we not do that in logistic regression? So anytime you are having your beta, your coefficient, we normally take the exponential of that coefficient. If you take the exponential of that coefficient, it is called odd ratio. The exponential of each of these parameters, this parameter that we are seeing here, the beta naught, the beta 1, the beta 2, up to beta n, it is called the odd ratio. So if you take the exponential of your parameter, it will give you the odd ratio. The odd ratio tells us how many times more likely or less likely something is to happen under one condition than other. Remember that in logistic regression, we only predict two outcomes. It's either yes or no. We have two outcomes. Now, what is the they may now ask you what is the odd of the outcome of this event. Let's say your own event is that someone passed the exam. They can now ask you what is the odd of someone passed the exam to those one that did not pass. So in logistic regression, we normally interpret the odd ratio alongside with the confidence interval and then with the p-value. But the odd ratio is very, very important. Let's look at the example 1 here. We want to check the study hour and then a student pass exam. If the coefficient, that is your beta, is 0.8, the coefficient that you are seeing here is not the probability. Please take note of that. It is not what? It is not the probability. Please take note of that. Now, if the coefficient, which is the beta, which is weight, the weight of that particular variable, the variable is the studying hour. The independent variable is the studying hour. But the weight or the parameter is 0.8. Now, what is the meaning of this? If you want to get the odd ratio, take the exponential of 0.8. If you take the exponential of 0.8, you are going to have 2.22. If you take the exponential of 0.8, you are going to have what? You are going to have 2.22. What is now the interpretation of this odd ratio? Now, look at this. For each additional hours, remember, in our normal linear regression, we normally say for a unit increase. A unit increase. But now, look at this now. For each additional hours of study, the odds of passing the exam, remember, passing the exam is 1. And let me say this expressly that your target, the positive one, always take 1. Now, the odds of passing the exam increase by 2.2 times. That is, if this particular student study for 1 hour, the chance, the odds of that particular student passing that exam is increased by 2.2 times. Now, let's say the person study for let's say the person study for what? For 2 hours. So what will be the odds? What will be the odd ratio? Now, that means that students who study 1 more hour, that is, let's say for instance now, the general study, let's say the teacher comes to class and they teach them for 2 hours. But any student that try to do additional 1 more hour, that person has what? 2.2 times most likely to pass the exam compared to those people that they don't even bother more to, they don't even bother themselves to study more hours. Now, let me now relate it to percentage. This is where I want us to listen and listen carefully. In interpreting the odd ratio, we have the standard, which is 1. Now, any value of odd ratio that is less than 1, we normally use the term less likely. Less likely. Now, any value of odd ratio that is greater than 1, we normally use what we call most likely. We normally use what we call what? Most likely. Now, if you have the value of your odd ratio that is greater than 1, like for instance now, what I have here is 2.2. You will subtract 1, that standard 1, you will subtract it from it. By the time you subtract it from it, we are going to have 1.2. Let's say you want to interpret your own odd ratio using percentage. That's why I'm explaining this. The 2.2 minus 1 is going to give you 1.2. Because by the time you run your data, those are the results that you are going to see. But how will you interpret it? So this particular aspect is as important as possible. Is that what? Is as important as possible. So by the time you subtract 1 from 2.2, you are going to have 1.2. 1.2 multiplied by 100 is going to give you 120%. Now, students who study 1 more hour are 120% more likely to pass the exam compared to those who don't. That is, any student that make additional effort to study an hour more, we have 120% chance, or 120 is more likely to pass the exam compared to those who did not make that attempt. So study 1 hour more increase your chance of passing the exam by 20% compared to not studying that extra 1 hour. That is extra 1 hour effort that student put into into his or her study gave he or she additional 120% chance, or likely. Don't let me use chance, because if I'm using chance, I'm talking about probability, and probability cannot be greater than 1. So more likely to pass the exam. So that is example 1. I have several examples here, so that if you don't understand this again, let's look at the second example. Look at the second example. If the odd ratio is 0.4 for using mosquito net and getting malaria, they want to check the relationship, the odd between the mosquito, those people that use mosquito nets, and then the malaria, and those people that did not use the mosquito net, how did they get the malaria? Now look at this interpretation now. People who use a mosquito net are 60% less likely. Now, let me take us back to what I explained the other time. I told us that the standard for the odd ratio, we have 1. 1 is is like a benchmark. That is why if you are using odd ratio and you are setting a reference category, we normally have reference category to be 1. That is the reason why they normally put 1. So the standard is 1. Now, the odd ratio that you are seeing here is below 1. Is below 1. So we are going to subtract this odd ratio from 1. Remember the other time, that one is above 1. We subtract 1 from it. But now this odd ratio here is below 1. So it's going to be 1 minus 0.4. 1 minus 0.4. And we're going to get 0.6. By the time you multiply that by 100, we're going to have 60%. 60%. That is, people who use a mosquito net are 60% less likely. Remember, it is below what? It's below 1. And when you have below 1, it's less likely. When you have above 1, it's most likely. Please take note of that. People who use a mosquito net are 60% less likely to get malaria than those who don't use it. That is, if you are sleeping under mosquito net regularly, there is 50% less that you are going to have malaria. That is, your chances of having malaria is 60%. So people who use mosquito net are 60% less likely to get malaria than those who don't use it. Now, let's look at the example 3. If your odd ratio is 1.8 for using fertilizer and getting high yield, for those people in agric. The first example is for those people in education. The second example is for those people in public health. Now, this example 3 is for those people in agriculture, into agric. Now, we have 1.8. Look at this now. Farmer using fertilizer are 1.8 times more likely to get high crop yield than those who don't use it. Now, with the knowledge of the odd ratio and percentage, I want someone to interpret this for me. For those people watching us from YouTube, you can type your own interpretation on the chat box. But for those our team here, I want someone to interpret this. Look at it and interpret this question 3 for me in terms of percentage. So if you want to interpret, you can raise up your hand and I will call you. I'm waiting. Thank you. Are we still together, please? Can you hear me?
Yes, sir. We are together, sir.
Okay. Now, please look at that and get me the results. What will be the interpretation?
The interpretation is written below, sir. It states that lawyers who attend the training are 2.5 times more
No.
likely to.
Look, wait. Look at the class test. I want you to,
Okay,
can
sir.
someone interpret this for me in percentage? The example 3. I want the
Okay,
example 3, the
that means
interpretation to be in percentage.
farmers using fertilizer are 80% more likely to get high crop yield than those who don't.
Okay. Any other answer, please? Any other answer, please? Ibukun, I'm waiting for you.
Okay, sir. So if it is in terms of percentage, so lawyers who attend the training are 150% more likely to win cases than those who don't.
Oh, good. Mr. Laide, I'm waiting for you too. Because those are the things that you are going to be dealing with. Once you do the analysis, you have your result. How will you interpret it? Yola for me, I'm waiting for your interpretation. Where's Damilola? Damilola, are you there?
Yes, sir.
Okay. What can you say about that?
Okay, for the example 3, farmer using fertilizer are 80% more likely to get high crop yield than those who don't. And for the example
Oh,
4
good.
is lawyer who attend the training are 150 times more likely to win the cases than those who don't.
Oh, good. Oh, good. Now, this is not the take home. This is the take home work. Give me the following logistic regression model for relationship between the examination pass and study hour. So I now have this equation now. Now here, -1 here is the intercept, then the 0.8 is the coefficient. Now, if the student studies for 3 hours, calculate the following. You get me the log odd of this. Number 2 is that you are going to interpret the odd, and you are going to get me the odd, and then you are going to interpret it. And then lastly, the odd ratio and interpretation. So this is where we are going to stop for tonight. So this is the theoretical part of the logistic regression model. So this is what we call the practical guide to logistic regression model. So starting from next week now, it's going to be purely practical. By then, I will have gotten a data set. So I'll get us a data set, and then make sure you have the R Studio installed on your laptop. The R Studio. Make sure you have the what? You have the R Studio installed on your laptop. So once you install the R Studio on your laptop, then I will be coming up next week, Sunday, 7 p.m. So I've marked today's attendance, and those people that are absent today, if they are also absent next week, they are going to be kicked out of the team. They are going to be kicked out of the team. So before I welcome question, any question from those people watching us live on YouTube? Any question? If you have question, you can type it on the chat box. If you have question, so Babalola Timle, go ahead with your question, please.
Oh, thank you, sir. It's not really a question. The last question given to us, I was unable to capture it, sir. So I don't know if you can just show it again, sir.
Okay, that's the question. Let me leave that for like 2 minutes while waiting for people to ask questions. I'm waiting for them from YouTube channel too, so that they can ask that question. And therefore, anybody that wants to join Donware data science team, Number one thing is that you will take one of our training. So I think we are starting quarter 3 by September 12th, 2025. So you are going to take in one of our training. So after that, after you've completed that training, then you can now apply for internship in Donwell Data School, and then the team, they are going to review it. If you are shortlisted, then they will welcome you to the team. So any question for me? Timileyin, how far are you done with this?
Yes,
Are you done with it? Okay. So this particular lecture will also be on our YouTube channel for public use. So anybody, if you have anything to do with the logistic regression and you don't know how to move about it, you can visit our YouTube channel and go over this video again. So it's public, but starting from next week, the hands-on is going to be for those in-house. So if you want to be part of the in-house, just apply for our next cohort that is coming up next month, September 12th. So thank you so much. Any other question, please? Contribution while waiting for people on the YouTube channel. Someone from our YouTube channel, how do we get the R Studio? Please, if you want to get the R Studio, just go to your Chrome, just type R Studio download and specify. R is a free source, so you don't need license. Unlike other statistical software like the SPSS and some other software like Stata, like SAS, that you need license, R is free. So you can go there and type it. But before you can install R Studio, you must install normal R. The normal R, just type R. First of all, install R, then install R Studio, because without the R Studio cannot work. So it's a free open source statistical software that you can download. So any other question from in-house or people watching us from YouTube? Any other question?
Yes, so my question is not really. I just wanted to know that this practical that you said you are starting next week, is it just for the in-house or internship? I think I was lost at that point. I didn't get what you said.
The practical is for the in-house, both our intern and then the team. Let me just put it like that. It's for the in-house. So we're not going to stream it. So it's for the
Oh,
in-house.
okay,
So
okay.
all this theory that you've learned, we want to practicalize it using a real data set, and then how do we demonstrate that using our programming language, R Studio.
Okay, sir. Thank you, sir.
So any other question? Any question from YouTube? Those watching us from YouTube, any question? Any question? Mr. Ide, are you still there?
Yes, I'm here, sir. No question from my end.
Mr. Ide, are you there? Okay.
Yes, sir. I'm
You
here,
didn't say
sir.
anything tonight. Okay, no problem. Mommy Adebisi. Mommy
No, no
Adebisi, are you
question.
there?
Yes, no question from my side. I came in late and there are a lot of back and forth from the
Okay, no
external side.
question.
So, but I'll take my time to watch and so that I can do my assignment.
Okay, okay, okay,
Thank
okay,
you,
no
sir.
problem. Okay, okay, no problem. Grace, any question? Grace, any question?
No question, sir.
Okay. Ibukun, any question?
No question, sir.
Ibukun, any question?
No question, sir.
Okay, no question. Okay, good. Boluwatife, any question?
No, sir.
Okay, no question. Dolafumi, any question? Okay, no question. So, lastly, Timileyin, any question?
No question for now, sir, but I think that next week when we start the practical aspects, there will be a lot of questions.
Okay,
sir.
okay,
Yes, sir.
okay, 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 okay. No problem. So, thank you so much for joining us tonight. For those people watching us from YouTube, thank you so much. We appreciate you. You can rewatch those videos again, and then if you're interested in joining our next cohort, we have our training coming up, cohort 3. We're organizing a cohort 3 training that's we're going to be taking us through Excel, SPSS, R programming language, and Python. How do you use them in data analysis and then to generate some little model? If you don't have any knowledge about the mathematics or statistics, that does not mean, because everything that we're going to be doing there is going to be practical using your laptop. So thank you so much for joining us from YouTube. So let me stop streaming now so that I can address the in-apps.